something, sure, but Wojciech asked me, so I decided to prepare some slides, which are kind of a tool session. I'm sorry, I'm going to present some tools. So, yeah, so it's about, it's a future work, future direction that I would like on myself to continue, but maybe you would like to join the group that will start working on some formal proofs using proof assistants. So I discovered I think I started 10 years ago working with the proof code assistant as let's say a student. And if you want to know at the beginning, if you want to see how you can use proof assistant in your community, you can say, we have some algorithms that are very difficult to prove. We have pen and paper proofs. And maybe for those algorithms, it can be useful to have some kind of formal proofs, even in a proof assistant, that everything is correct. I will give you an example of such an algorithm that was found to be correct, but at the end, after 14 years, the algorithm was proved to be incorrect about measurements. So I think it's important, typically, if you want to prove the correctness, termination, or provide some complexity bound, if you want to be sure that everything is okay, it should be interesting to use a proof assistant. Moreover, it provides for the not for many applications. It can be interesting when you make a proof to provide constructive proofs, meaning that if you want to prove that some objects are decidable or constructible, for instance, if you want to prove that something is coverable for a Petri net, then you can compute such a sequence proving that it is coverable. Somehow you need to prove that some algorithms are really computing what they should do. So we are really computing a sequence of of actions proving some reachability property or coverability property. So that can be used for algorithms, but proof assistants can also be used for naturally for proving pen and paper proofs. And Sylvain mentioned this problem that we can have when we are using some lower bounds on top of some other result of lower bounds. We can have several reductions because the model you would like to encode your problem is really odd, so you are using some special encodings. And sometimes it's difficult to be convinced. I think if you are as a reviewer, I'm quite sure that for some papers, you think, oh yes, it seems to be correct, but I'm not so sure. It's very too technical. And I think for this kind of result should be interesting. I agree with Sylvain to have some formal proofs. Moreover, it provides some strong guarantees that the results are correct, which can be, from my point of view, it's an interesting perspective. So the question is, okay, this is the two kind of application. The question is how to do it in practice. And the main problem is that if you start from scratch and you want to cock, for instance, because I'm using cock, if you want to prove some results about, for instance, Petri nets, you are in trouble because you need to develop a lot of techniques. There is some library that can help you, but somehow, if you want to do everything from scratch, it can be a long work. So I think it can be interesting to develop some code library for community. But I will come back to this just after. So during during last week, I was in Madrid, and in fact, Pierre Gonti, who is in Madrid at TLU, invited me to make a presentation about something about Petri nets. And during my stay, I discussed with Alexander, and so he was interested by what we did in Coq, because he is using Coq also in his research. And so I copy-paste what he provided on his webpage. It's not what he said when I discussed with him. But he mentioned something that can be interesting for our community about why we should produce some Coq proofs. It's not just to be sure that everything is correct. There is another important application, and I think this application should motivate the community to develop some code. So the idea is the following one. Assume that you try to make a proof that the reachability problem, for example, for vector addition system is decidable in Coq. So you start writing your proof. There is a huge part when you make a Coq proof. There is a part which is writing the proof, but also a part which is very important is the modelization of the object you are going to work on. And so you start by modeling, for instance, let's say the automata or the marking graph sequence that occurs in the reachability problem, the algorithm for the reachability problem. That at some point, maybe you will have a problem, you will be in trouble because proofs that you would like to make to obtain become very painful. Because somehow the Coq assistant prover asks you to prove some very technical lemmas that are clearly true. And you do not know why, but you always have to repeat the same kind of construction. So there is two possible ways in that case. Either you stay on the train, so somehow you continue, you develop some new techniques, new tactics. Because in Coq, when you want to make a proof, somehow either you make your proof step by step, or you craft a new tactic, a new way of proving your results. So this is a possible way. If your proofs are very difficult to obtain, you can develop new tactics and you can call those tactics in order to help you to make the proof. Or there is another way. Is to decide to come back because it's a dead end. You decide to come back to the original model you developed. It's because somehow, if you have troubles with your proofs, maybe it's because your model, the model of the object you would like to manipulate, is not the right one. And I like this idea because somehow, somehow if you want to make a simple proof, you are going to think about the way object should be defined. And the way this object should be defined will provide some a new flavor of the kind of object you manipulate. And I think this is quite interesting. So Alexander used this technique in order to develop a new theory about separation logic, and it was quite successful. It already new results, but those new results come from a new modelization of what is the content of the memory, what is the heap of the memory. And he find out this new technique, in fact, by developing some proofs about the classical separation logic, and find some problems using the classical definition of the logic. So I like this idea, and I would like to mention, I think it's an important property of what we can do with an assistant, a proof assistant. Somehow it's a way to design how not only formal proofs in Coq, but also how pen and paper results should be presented, on which mathematical object we should present those results. There is an algorithm, a variant of an algorithm that was recently proved, tried to be proved several times. I presented the picture. I'm sorry, Mikael, you're cutting. No? Maybe not, so it's good. I'm not responsible of that. I think it's when they take the picture, it was cut like this. It's quite bad because there is some space over there. So I put this picture because I would like to say that among those people, several of them, me included, I tried, I was working on an algorithm, it is the KLM algorithm, decomposition algorithm. So Roland presented an algorithm based on the KLM decomposition. And naturally, this kind of algorithm is parameterized by the property you would like to prove. And the good question, if you want to have a model of that algorithm in Coq, so if you want to prove in Coq that the reachability problem is decidable, somehow you need to find a good abstract way of what is this decomposition. So, and I think there is do in this area. And so I would like to somehow to formalize and concoct this algorithm, this decomposition algorithm. It's a huge work because there is several techniques that are used for this. I would like to point out some related work because it's not a new project. So some people first provided a proof of correctness of the Carpé-Miller construction. I don't know if you know this Carpé-Miller construction. I have some slides. I can show you something about the Carpé-Miller. So the Carpé-Miller algorithm is computing. This is really bad. So the Carpé-Miller algorithm is computing the donor closure of the reachability set of a Petri net. So you have here a Petri net, and somehow you would like not to compute the set of reachable configurations, but configuration that can be covered, which is the donor closure with respect to the point-wise order of the places. You would like to compute the donor closure of the reachability set. So you remember yesterday I provided my failure, during my failure session, I provided some result about the maximal element of set of configurations introducing some omega. When you have a donor closed set, there is always some maximal elements that are called ideals. And those maximal elements can be computed with, for a Petri net, with an algorithm that is called the Carpé-Miller algorithm. I'll show you some steps of the algorithm. So you start from the initial configuration, and you are going to compute with a tree the reachable configuration by executing the transition step by steps. And in that algorithm, in order to obtain the termination, if you see a node that is larger than an ancestor, you are going to put some omega on places that are strictly increased by the sequence. So as you can see, if you develop your tree, you get something like that. You see this node is larger than this one, component-wise. So you are going to put an omega here. You will get this tree. Then you can continue to develop the tree on this side. This node is smaller than this one. Okay, so the idea is to remove that node. You will get this node. And you continue the exploration. And every time you obtain a node that is larger than another one, you are going to cut your tree. And this algorithm, which is not exactly the Carpé-Miller algorithm, it was an improvement of the Carpé-Miller algorithm given by Rafael in 1991. And this algorithm terminates with this tree. Okay? And as you can see, this tree is not the closure of the reachability set because there is no omega in that tree. There is no omega anywhere. Okay? But there is some omega there is some components that are unbounded. For instance, this component here is unbounded. So it means that this algorithm is there is a bug in that algorithm. There is a subtle bug. And the bug in the original Carpé-Miller algorithm, the bug was not present because the cutting operation, when you say I have a node that is smaller than an already explored node. In the Carpé-Miller algorithm, it's just when a node is somehow covered by an ancestor, but not covered by another node in another branch. So, but this algorithm was introduced in order to optimize, to obtain an optimized version of the Carpé-Miller algorithm. And there is a subtle bug in that algorithm that was proved only 14 years after. The algorithm was published and used in several other tools. So this kind of problem shows that even if a proof seems to be correct and the algorithm seems to be correct on some examples, and in fact many examples it was correct, there exists an example which is this one. I think it's the minimal one for that Petri net, which is not so simple. I mean, this Petri net exhibits a bug in the algorithm, the optimized version of the Carpé-Miller algorithm. So let's come back to the so what was done in that paper is a formalization in COC of the correctness and determination of the original Carpe-Miller algorithm. But maybe you know that the Carpe-Miller algorithm attract, as soon as we discovered that there was a problem in the original algorithm, I mean not the original one, but the optimized one, some people try to find a way to patch the algorithm in order to have a correct one, which is still optimized. And they finally succeed in finding such an algorithm, and we decided with a colleague and a PhD student, David Sakat, my colleague at Tipuyer, who will finish his PhD soon, in summer. In fact, we decided to look at this state-of-the-art Carpe-Miller algorithm and try to make a proof in COC of a recent algorithm. And in fact, it was possible to do the job, starting from the library implemented by those guys. But it was just for the Carpe-Miller algorithm. I mean, it requires some stuff, but it was just for the Carpe-Miller algorithm. And now, what we are interested in is to develop a library for the Petri nets. And I would like to give you some demo for the moment. So it's who knows who already used the COC in practice? Okay, so yeah, so it's okay. It's good. So it's good because you will see what is the form of a proof file. So a proof in COC, it's like it's like a program. Okay? So you can have library, you can write your own library, you can import library, it's like a programming language. I would like to show you what is the definition of a Petri net that we use, and you will see it's quite similar to what we should write in the paper. We say, okay, a Petri net is a set of place, a finite set of place, which is the definition of file type. Finite set of transitions. We have a function that provides the predecessor of the successor, pre and post of the transition. We define what is the marking of a Petri net, just a function that maps any places of the Petri net to a natural number. And if you want to define what is the semantics of a Petri net, you just have to explain what is the next, to define what is the next marking when you execute a transition T, and you say, in fact, either the predecessor, the marking is large enough, and in that case, you will say the successor is a sub marking, which is defined by removing the pre and adding the post. Otherwise, there is no marking by executing the transition. And this way, you can define, thanks to some notations, interesting way to describe your semantics and properties. For instance, if you want to say something is reachable, you can say there exists S in that case a string of transition, such that from the initial marking you can execute this string and get M. The coverability will be defined thanks to the reachability, and all the properties can be naturally defined. And then, as soon as you have defined your object, then it's placed for proofs. And the proofs, I will not enter in the proof, I will not show you, but some proofs are not so ugly, as you can see, if you want to prove, for example, this lemma. So one say this lemma. So this lemma say, for example, the marking M1 is always smaller than or equal, component-wise, the marking M1 plus some other marking M2. And here you have the proof. So I will not enter in the proof because it's not the purpose of this presentation. And just to mention that, so we started developing to develop that library, and it's really, if you want to join the project, I think it's really interesting to form a small group of people in your lab that meet every week, for instance, 1 hour a week, and during this 1 hour, as a small group, you can say, okay, we are going to develop this theory or to develop this problem. And it's quite interesting. I mean, in my group, And some people say, this working group on COC, this working group is the best working group I ever assisted. So it's interesting somehow. So you can develop step by step some results. So for the moment, just to let you see what we are doing. So we are trying to prove the Rakov techniques, and in order to, as I mentioned, before trying to make the proof of Rakov, which is somehow an induction of the number of places of your Petri net, you need some operation like projection. You have a Petri net, and you would like to keep only a subset of places of the Petri net, and you would like to provide some properties of the projection of the Petri net. So the projection can be defined quite easily. You have a function from a set of places Q to the original places of your Petri net, and you define the projection of the Petri net just by using the same set of transition, but the two functions pre and post are just defined as composition with this function that project away some places. So we started developing the projection, and as you can see, step by step, every week we develop pour les bas. So the lemma can be analytic. Naturally, you can say, okay, we will see this lemma later. I think this lemma is true. Let's continue on the interesting part, and let's provide this lemma to some master student. So this is the idea. Okay. So in that session, I wanted just to give you a flavor of what we can do with an assistant prover like Doc. And let me come back to the presentation. And I think I have nothing else to present. So thank you. For your attention.
Questions?
Aren't limits in the power of these provers to prove termination for algorithms which run really slow? And I mean like no primitive recursive or...
This is a good question. Yes, you can, in fact, you can define what is the Ackermann function just by proving the inductive way or inductive way how to define the Ackermann function. But you can execute code and ask what is Ackermann of something, and in that case, naturally, you will never get the answer. But you can define it and use it in your proofs. You can say, because you will have some lemma proving that some things is bounded by some Ackermann function or.
So Ackermann function, you can prove it determinates with this system, yeah? But I wonder if you.
So in that case, if you want to prove the termination of, let's say, a program that is based on the fact that the vector of integers is well-founded, is the, let's say, the lexicographic order. If you want to prove that, then you will make the proof by, it will be proved by induction on the well-founded relation. So at the end, we say, okay, you can define your algorithm. I mean, it depends on the way you define your algorithm, but it will accept, even if the computation is quite slow, it's Ackermannian, it accepts the proof because it terminates. So you can do it. There is no real limitation of what you can do. You can also introduce some axioms in order to have the classical logic. But this is not the way we would like to do the library. We would like to have something constructive.
I have a couple of questions because I have been conducted together with Tobias Lipkov a similar project, but it's more about visual automata, and instead of Hockey's Isabel. So I just wanted to share experiences or ask you. So the first one is it possible to kind of automatically obtain an implementation from the proof?
Yes.
Can you generate code from the...
This is why we are interested in constructive proofs.
Yeah.
If you prove that your algorithm, your property, some object exists thanks to classical logic, you have no way to construct your object. But if your object is given thanks to a constructive algorithm, then you can extract an algorithm computing the object. But in that case, the algorithm that you will obtain naturally will depend on the way you make the proof that the object exists.
Have you tried it with the Carpenter?
Yes, for the Carpenter, so we try it, and but it's still a work in progress because somehow, in order to prove that this algorithm, this one, state-of-the-art algorithm, Carpenter algorithm, is correct, we introduce. In fact, there is many non-deterministic choices in the original algorithm, and those choices must be somehow instantiated. So, for instance, the classical problems that either you implement a DFS or a DFS. You have to select which one you. If you want to prove that your algorithm is correct, whatever the implementation you consider, you will introduce some non-determinist way of developing your tree. So this is the way we prove the correctness of our algorithm. So in particular, if you want to have an implementation that is extracted automatically from the proof, at some point we need to add a kind of scheduler that will make the choices, that will make the non-deterministic choices.
And our experience was that it takes a lot of work to make it reasonably efficient.
Yes.
Because you get functional implementations and all that. You also have a problem?
So for the moment, we do not have extractions.
Right.
So we will see. Hopefully it will be slow. I mean, not so slow compared to the pipeline.
I was curious about another point. The experience in the Bushy project was that, well, you proceed at the beginning, you just want to prove some, or implement algorithms, or prove algorithms correct for simple operations, and then comes something else, and you do it with the help of the students. And every time the student comes and says, no, the library for defining Bushy automata has to change. You are not defining Bushy automata in the right way.
Yeah, this is the problem.
So how stable is the Petri-net definition?
So, in fact, the Petri-net definition, it's very curious. If I come back to the code, in fact, so this is not exactly the definition we consider in your paper, this one. Petri-net, because it was defined somehow in that position it was not possible when we project away a Petri-net by projecting thanks to a function that reduce the set and reduce again. So with two projections, is it equal to the Petri-net I obtain to the Petri-net I obtain by reducing by the two functions, the composition of the two functions. So we get the trouble proving that the two Petri-nets are equal. So in that case, it was possible to continue to stay on the tray and introduce what is called equality up to some morphisms and stuff like that. But we decided to go in another way. It's really curious. We just modify a little bit the definition of the Petri-net. We push a button, and all the proofs that that was already written for the Carpe-Miller construction was okay without modifying anything. So it seems that the new definition we have, which provides this equality directly, is the good one. So it provides a way to improve your model. So even if the model seems very simple, I remember that it was 10 years ago when I tried to do in Coq the definition of Petri-nets. First, I was trying to define a marking, like a sequence of numbers, but it was horrible because every time you need to have a proof that the lengths of when you make the sum, the lengths of the two cycles, the two sequences are the same. So in order to obtain the right one, you need to think about how to define what is a marking, what is a Petri-net. But I like this definition. Now I think this definition will be stable, hopefully. We will not modify it.
And then you want a final question. So our experience is also, that you cannot keep up. I mean, the time you need for the proof is kind of one or maybe more orders of magnitude longer than the time you need for changing the implementation. So the problem is that the next guy comes and says, oh, I could the algorithm can be made faster by introducing this.
Yes.
And then, okay, it's no longer the same algorithm, so the proof is no longer valid. And adapting the proof takes much longer than
You can
and there is this alternative, which would be to have even for coverability. So if you are saying, is this marking coverable, that the algorithm gives you a proof.
Yes.
Right? And it could be, if it is coverable, a sequence leading to it, and if it is not coverable, then an semi-linear invariant, right? Is there any idea how to do this for coverability or reachability maybe even?
So somehow you, as I mentioned, so you define what does it mean that being coverable, and as you see, the definition will not change. I mean, it's always this definition. And the question is how to implement the coverability or the reachability, and you can have several implementations. You can, I don't know if I also.
No, but for coverability, I mean, you put it very easily. You have a Card-Miller algorithm,
Yes.
right?
Yeah.
And if it is not coverable, then you get as output a semi-linear set such that
even
close.
downward close set.
Yeah, or downward close set. Yeah, in this case it would be a downward close set.
Yes.
And you can have an independent unit which checks that, right?
Yes, you are right.
And that's not very difficult. And this is an alternative to proving the algorithm correct. So the algorithm may not be correct, but you know that if there is a bug and it gives you a wrong result, you will detect it.
Yes.
I mean, as long as you trust this. And trusting that module is probably not so.
There is several ways of trusting algorithm. Either it's an algorithm that you could correct. I mean, it's an algorithm in C or in Python or Java that you could correct next to the proof. Or it's an algorithm that is correct because it is extracted automatically from the proof. Or it can be an algorithm that is maybe incorrect, but I can verify. I have a way to verify the output.
So I think this is very interesting in theory. For anything that would have to do with practical applications, I think the other is much
the other side is better.
Because you can keep developing the algorithm without having to worry about the proof.
Roland? So what is the assistance that I have by Coq of sort of getting these definitions in there? I mean, I have to type it myself all the time.
Yes. If you have, if you start Coq without loading no library, you have almost nothing. You have neither true nor false. I mean, you must define what is true, what is false, and develop your theory.
But I have a front end, it's the LaTeX paper, in which I have written the proof, maybe not at this level of precision. Is there any infrastructure that could make use of this and, how to say, I mean, I'm already writing the sort of inductive definition somewhere there.
Yes.
It could understand it and make an appropriate Coq definition.
It should be interesting for this.
No, because this is somehow, I mean, you know there's this programming by example, right? I mean, you give a bunch of values and you ask for a function that with this input gives you this output.
Yes.
But now my input is much stronger. No, it's the whole paper. Now, I'm roughly serious in the sense that, I mean, there may be 5 ways of turning this is a set and this is a part and so on into a Coq definition. And maybe there could be an engine, because, I mean, honestly, I don't want to do a Coq here. But maybe I'm
But
interested.
maybe some others will do Coq proofs that you can rely on.
No, but maybe it's also interesting to write this engine, and the engine presents to me, I just have to click yes or no. Do you want this definition? No.
That's cool.
So maybe I make a small comment on it. Like, I don't know Coq, I'm not using it, but once I've heard from a student that's doing some proofs that he's using ChatGPT to help him generate code. I think in Coq, but I'm not sure if he was using Coq.
For Coq, I think it doesn't work for the moment well.
Okay.
You have to use it.
So maybe he was doing he was using some different code.
You see, what we write up already has a high degree of structure and precision in it. So,
Okay.
marker. No, just one is enough. Yeah, thanks. It's okay? What about this one? Wojtek, can you rotate a bit? Right. No, like rotate in this direction. Yes. Okay. I will tell you about two future directions which I find interesting. The first one is actually a bit like a failure report. So I think this is a very interesting direction, but I think it's very hard to pursue. So yeah, we are all familiar with language equivalence. There's like a kind of typical equivalence for automata or automata with something. Yeah, automata with pushdown, automata with counters or vas and so on. But there is a similar notion, let's say. So you may say that instead, because if you just look at language equivalence, you just look whether a word is accepted. But you don't care whether there is one accepting run or more accepting runs. So you may say you actually count accepting runs, and automaton defines a function like from words to numbers, right? A bit like in a weighted automaton, but I'm looking at a very simplistic weighted automaton which just for each transition has a weight 1, right? So I'm saying so automaton defines a function from words to the numbers, and the number is how many accepting runs are there for this particular word, right? And you can ask now whether two automata are equivalent in this sense. So whether for each word they have the same number of accepting runs. So this is there are many names for that, but I will use the term multiplicity equivalence. And for example, for finite automata, for non-deterministic finite automata, language equivalence is p-space complete. And in this multiplicity equivalence, it can be naturally reduced to the equivalence of weighted automata. And then this can be, if you just have two weighted automata, you can kind of subtract one from the other. And you can ask if you have automaton A and B, you can ask, you can say A equals B if and only if A minus B equals 0. So this naturally reduces to the so-called zeroness problem for weighted automata, and using some not very hard linear algebra, many of you know it, probably you can show that this is in polynomial time. So for finite automata, multiplicity equivalence seems to be simpler than, just is simpler. Well, okay, unless P equals P space. But seems it's simpler than just language equivalence. And for more powerful automata like pushdown automata, we know language equivalence is undecidable. There is a conjecture that maybe for multiplicity equivalence it is decidable. Of course, this would be pretty hard because for deterministic automata, for each word you either have 1 run or 0 runs, right? So deciding multiplicity equivalence for, let's say, pushdown automata, it would be harder than deciding language equivalence for deterministic pushdown automata, which we know is pretty hard. But, so we were thinking about this in Warsaw in different groups, with Lorenzo, with Philip, with, I think, Ismail as well, and we asked some guys from mathematics, and we miserably failed. So we didn't thought, so first step to pushdown automata would be to consider some more restricted model. You can consider, let's say, one counter automaton with 0 test. But okay, let's exclude let's exclude 0 test. Let's consider just automaton with one counter, like a vas counter, so one-dimensional vas, or even something simpler,
automaton with one integer counter, right? And let's try to look at this model. Let's try to decide multiplicity equivalence for that model, and we had completely, we had nothing for that. Recently, Lorenzo, so our idea was just to try to get decidability for multiplicity equivalence for any model which is richer than finite automaton. Lorenzo recently considered so-called BPP nets, so like communication-free Petri nets. And Lorenzo has shown the decidability for, multiplicity. What you have shown is actually probably zeroness for weighted BPP, right? But which implies, which is probably almost equivalent to multiplicity equivalence for BPP nets. And the result actually shows, if I can say it, like Hilbert's basis theorem. And as far as I understand, it's like a pretty straightforward application of Hilbert's basis theorem. But already at this pretty simple setting, we need Hilbert's basis theorem. So why I find this interesting? First of all, this is another notion of equivalence which may have this property a bit like bisimilarity, that it's somehow more robust than language equivalence. But second reason is that I think you very quickly touch some seemingly deep mathematics. So what is known, so I think ICAL 2020, a few people from France, I forgot names, maybe you remember, Lorenzo.
Around Boston and collaborators.
Yeah, for authors. And they have shown in particular that for integer vars over one letter alphabet, this problem multiplicity equivalence is decidable. So already they used holonomic sequences for that. So these are like power series which are called also D-finite. So they needed pretty sophisticated technology to prove one letter case. I can tell you one, so when we were thinking about that, I can tell you one case in which we formulated some conjecture and found some theorem about Laurent series, Laurent polynomials, which, so the conjecture for one state automaton is true, but the only proof we know, I mean, it's hard to say we know, the only proof we've seen, it was using some complex analysis, or maybe you should say functional analysis, but you go into complex plane and you count some, look at some traverses in complex plane and make some calculus of it. And so I think it was just one state, and I think one letter, and one counter.
How many automata would make this one?
Okay, so let's draw one automaton like that. So what you may have, okay. So it was for weighted automata. Yes, but actually, I mean, if you count runs, you can say you have 3 transitions like that. So you can say you have a weight 3 there. Yes, so. And I think we wanted to solve zeroness. What is a zeroness problem? You are given weighted automaton, and you ask, is it true that this automaton outputs 0 for every word? So this is like equally, I think you can interreduce from multiplicity to that problem. And you may have transitions. So for example, you increase your counter by 2, and you have weight equal, let's say, 3. And you may have another transition which, let's say, decreases your counter by 1, and your weight is 5. And let's say you have another transition which, let's say, I don't know, decreases your counter by 3 and weight is 7. And, well, okay, I hope I will. And you have one letter, so the question is there such a number of letters? So for which, if you sum up all these runs, you get actually non-zero value.
In the weight or in the counter? There's some constraint on the counter, getting the counter back to 0, right?
Yes, so you start in counter value 0 and you end in counter value 0. Right? And so with all your, yeah, so what was our conjecture? So it's obvious to see that if all your, it's obvious to see that if you have a, yeah, let's see, all the modifications on the counter are positive, so you always go up. Starting from 0, you will never go back to 0, right? It's also obvious that if all your modifications are negative, you will never reach 0, so then this is the 0, then the automaton has zeroness property. So we conjectured that if you have some positive transition and some negative transition, then you always, then this automaton has never zeroness property. So it's obvious that, for example, if you have like +2 and -3, so then if you fire this transition 3 times and that transition 2 times, so you have a word of like 5, this run like 3 times this plus 2 times that, it will come back to 0, and the weight of this run will be non-zero. But maybe you have other runs such that you sum them all, and then maybe in total you have something like 0, right? So I can tell you how you can solve this particular case. So for such an automaton, you can assign something which is Laurent polynomial. What is a Laurent polynomial? It's like a polynomial, but it also has negative powers of x. I will show on this example. So what you have is you have 3x squared. I hope I'm, yes. So this corresponds to that, right? So you take a weight, you write 3, and you write x to the power of your effect of your counter. Then, for this transition, you have, I guess you suspect what I write, 5x minus 1, plus for that transition, you have plus 7x minus 3. So in some sense, this polynomial represents what happens if you fire just one letter A.
Okay, how weights are positive? Okay, so
Weights are, in that example, weights are positive. I think they might be negative. So why this is, why such a polynomial makes sense? Because if you fire one A and then again one letter A, so somehow this transition corresponds to taking a square of this automaton. Because if you take this transition and then this transition, the weights multiply, but the counter effects they add each other. And this is the same what happens here. So the coefficients multiply each other, and the exponents they add each other. So if you want to know, for example, what's the weight of a word of length 100, you should raise this polynomial to power 100 and look at the coefficient, which is like, which is together with x power 0, right? It's look at the constant coefficient. And constant coefficient in this Laurent polynomial raised to power 100, this is exactly the weight of a word A 100 times. Is this, do you see this, or I should somehow convince you more? Yeah, and we have looked for that, and it seems that there is such a lemma, such that if you have a non-zero Laurent polynomial, which is such that not all the exponents are positive, not all of them are negative, then there is such a power, such that actually the constant coefficient is is non-zero, and kind of we tried to read this, and I failed miserably. I was Lorenzo, maybe not miserably, but I'm not sure. Have you understood?
This falls in a class
What?
that is decidable, no?
Hmm?
This zeroness for this. There's so many constraints here that this falls under the scope of the ICAP 2020 paper. This was
that's
part of an effort to understand differently the desirability result.
Mhm.
In this particular case, the answer is always yes, or always no, right? And it was very
Yes.
structural.
So-
just for the powers of the exponent.
For this particular automaton, we managed to generalize it, so we managed to prove it for many letters. But I don't think it's a lot of success. Okay, so that's just part one. How much time I've used?
Let's say you have 8 minutes.
Hmm?
We have like 8 minutes.
Okay. So we've tried in different configurations. At the end, I decided I'm too weak for that. I need some people stronger in algebra. But I think I just wanted to share it with you. That I think probably we need some deep results from. So maybe non-commutative algebra somehow appears here, because if you have one letter, things are commutative. But if you have two letters, A and B, then what happens for a word AB might be different than what happens for BA. And non-commutative algebra is hard. So maybe we can find some deep results in non-commutative algebra. Maybe we have to work with people from that field, and they can help us. But I think that these problems might be decidable, and maybe there is something deeper hiding beneath the surface. So that's one thing. And another thing is rather, so recently we worked with Keveli, with Vincent. Where is Vincent? Vincent is there. On some, so this is related to this problem of root of a vast language, which I've told you.
Maybe before you change topic,
Yeah.
this feels very similar to the kind of problems people have with the transducer equivalence and coding all this into some kind of polynomial automata where sameness is decidable through computing with high-risk explosion. In the end, well, you have hypothesis in this type of algorithms. I don't know, can't you encode all this into the sameness problem for
Into
for
transducers?
polynomial automata? Or it's similar to what people also developed for transducer equivalence. And then there were some limits. They could go some way, and then
I think, at least I haven't tried much in this direction. Lorenzo, have you looked?
So these are kind of Laurent polynomials. There is this cancellation of negative powers, and for the Hilbert approach, this is not there. There is no negative powers. So I don't know. It doesn't fit the bill.
the wrong polynomials is because you're using Z counters. If you wanted actual counters.
No, if you make the effect of a decrement.
Oh, but yeah, okay. There are ways to encode from one to the other.
Yeah, maybe. This Laurent polynomial, I just wanted to give you some very simple example, what happens in already a very simple example. But possibly we can have a look whether these people developed something useful for us.
You have colleagues who have worked on this
I bet
approach to transducer equivalence. It feels a bit
Oh, I know this proof in transducers by Hilbert's basis theorem. I think that's maybe what can be the same kind of paradigm can be applied to BPP nets. So that kind of Hilbert's basis theorem gives you a finite representation of that. But I think here we need kind of much more. That's my feeling. But yeah, we may think about that. So another direction. So we started working about that, and it's pretty fresh. We work on that since a few months, but I think that might be an interesting direction. So recently, Roland and Eren solved regular separability for vast languages, and this kind of, in my mind, closes, but maybe not entirely closes, but makes some. end of some story, like our search for regular separability for vast languages, for some subclasses. Of course, there are still interesting questions, like for example, what if you have a vast language on one side, contextual language on another side, and then can you regularly separate those, and so on. But this kind of motivated me to think what other separability questions we may think about, and then Vincent said, okay, what about, for example, separating by first order definable languages? And so you may imagine the following decision problem. So we are given two integer vast languages, and you ask, are they separable by first order definable language? Right, so usually if you just ask, so let's stop for a moment. Let's imagine that you are asked about the problem. You are given an integer vast. Does it recognize a language which is first order definable? So this you can solve. I mean, you can try to approach this like that. You ask first whether this language is regular. I'm not sure. This is probably undecidable, right? I'm not sure.
Yes.
Yeah, but in principle, yeah, if you have three classes, one inside the other, you first for a language in the most general class, whether is it in this. Yeah, let's say we have three classes, like F1, family 1, family 2, family 3. So if you have a language in here, you want to know whether it's in F3. You can first ask whether it's in F2. If not, then obviously it's not in F3. But if it is in F2, then you compute somehow representation in F2, which is possibly possible. And then you you fire an algorithm for languages in class F2 for deciding whether it's in F3, right? So you can do it step by step. But if we have these separability questions, you cannot. We know algorithm for regular separability for the vast in languages. There is an algorithm to input regular languages where they are first order separable. Thomas Plass and Margaret Thun they have worked a lot on this kind of problems, and they designed many separability results for various subclasses of regular languages, which they know how to decide. You are given to regular languages, are they separable by a language in that family? But this is not compositional. So I think that this is in general might be an interesting question to consider different languages which are not regular, like integer vast languages, I don't know, one-dimensional vast languages, whatever, coverability vast languages, and ask, are they separable by some family which is included in regular languages? And so, for example, first order definable languages, but I don't know, first order with two variables definable, or so we started from some very simple class which is called locally testable. Language is locally testable if you can describe it by saying it has this prefix, it has that suffix, such an infix is in there, and you take Boolean combination of such conditions, right? And like this motivated us to ask, so some baby version of that was this problem that if you are given two, let's say, Z-vast languages, do you have a word which is in the root of the first one and also in the root of the second one? So that was baby version. So maybe why I think that it's interesting, because I think you might be forced to use two different kind of techniques. One techniques from our community, like for infinite state systems, I don't know, semilinear sets, some kind of pumping amalgamation, you know what we do. And another set of techniques from like inside regular languages. They do this algebraic theory of regular languages, yes, you define syntactic monoid, and then you do some L classes, R classes, Simon decomposition, Shimon decomposition, and there are other tools. And I think we might be forced to merge this stuff, and maybe this is interesting. I think separability might be just only one example of family of problems which can be asked here. Yeah, Aaron?
So interesting because I think all of us regular separability results rely on some kind of modular accompanying. But other languages are specifically those that do not do this.
Mm-hmm.
So might give some other insights.
So I think we should, I'm definitely interested in pursuing this direction. I hope we'll not find out soon that all these problems are undecidable, but my feeling is that they are decidable, we just lack techniques how to merge these two words. So that's, and possibly, I don't know, maybe some uniformization questions may also be put into this framework, maybe more questions which are kind of cannot be composed into, decomposed into two steps, right? Two regular and then inside regular. Okay, that's it. Any questions?